Hey guys, welcome. Yeah, so I hope you're having a great day, and may the Lord Jesus Christ bless you, bless me in this video. And yeah, so in the previous two examples, I said previous two examples because there were examples 0 and 1, so that's two examples. We saw the formal limit definition of the partial derivative. In particular, we said that the partial with respect to x of some function f of xy is defined as f sub x equaling, it's abbreviated as f sub x, but it's defined as the limit as h goes to 0 of f of x plus h comma y minus f of x all over h, right? So in example 0, with some awesome visuals, I explained why this makes sense as defining the partial with respect to x. And so I showed you where it came from. And then in example 1, I showed you how to use this formal definition, so the limit definition of the partial derivative, on the function f of xy is equal to x squared y, right? So I showed you how to use this to find the partial with respect to x using the limit definition, and the partial with respect to y using a very similar limit definition. So we did that on this. But then at the tail end, at the very end of example 1, I showed you that you could find the partial with respect to x of this function f of xy without using this limit definition, without appealing to the limit definition. So I showed you a shortcut in essence. And because the shortcut was demonstrated on this very simple function f of x comma y, it's not really sufficient. And therefore, example 2, where I will show you harder examples on how to use the shortcut to find partial derivatives. Let's first do it on this function. So on this function, let's first find the partial with respect to x. Right? What we said at the tail end of example 1 is when you're finding the partial derivative with respect to x, you treat all other variables as a constant. In this case, there's only one other variable, y, but even if there was more than one other variable, you treat all other variables that are not x as if they were constants. So here, y cubed is a constant, and this y is a constant, and obviously 2 is a constant. Otherwise, we take the derivatives as we did in Calc 1, as usual. So that means that we do 2x y cubed, right? Remember, y cubed is a constant because we're taking the partial with respect to x. And then plus, we're done with this term, right? And then plus, moving on to the second guy. So it's going to be, well, we could leave out the constant 2, but then the derivative of cosine is negative sine. And the reason why we need to take the derivative of cosine is because in the argument of cosine, there's an x. So this cosine is a function of x, and therefore we need to take the derivative of cosine. So we go negative sine of xy, but then this y is a constant, so to finish taking the derivative of cosine of xy, we need to multiply by y. So cleaned up, that'd mean the partial with respect to x, denoted by this, right, is equal to, it's minus 2y sine of xy, right, like that. So we are done doing the partial derivative with respect to x for the function f here. Yeah? Okay, so just like how you have second derivatives, you can talk about the second partial with respect to x, right? So what you would do if you needed to find the second partial with respect to x, right, and it would be denoted as fxx, like this, right? What you would do is, well, first find this, which is this, and then take the derivative of this with respect to x again. So this here would equal, well, again, anything that's not an x in here is a constant. So we go, that's 2y cubed, right? And then minus 2y, both 2 and y are constants. And then again, sine inside it has an x, so this is a function of x, and so we need to take the derivative of sine, which is cosine, and then xy, but then to say we're done, we need to multiply by the constant y, right? And so then we have that fxx is equal to 2y cubed minus 2y squared cosine of xy. Yeah? Okay, cool. So then let's do what we didn't do, which is the partial with respect to y. So that's fy. There's this harder example that we're going to get to in a second, and I'm not going to do all of these on this harder example. I'm just going to do the partial, say, with respect to x, and that should suffice. But yeah, I will get to it. It's not up there. It's chilling. Okay, sorry. So back to the original, and the partial with respect to y this time. And remember, as I said in the previous examples, there are other ways of denoting the partial with respect to x or y. And so for the partial with respect to y, we could write it like this, right? And so this here, which is the same as this here, which is the same as, in case you missed all the different ways to denote it, is equal to, well, we treat anything that's not a y in here as a constant. So that x squared is a constant, so we go 3 x squared y squared. We're done with the derivative of there. And then plus 2 times here, cosine inside it has a y, and therefore this is a function of y, cosine. So we go 2 and then negative sine of xy, but then this time x is a constant, so we multiply by the constant to say we're done. So cleaned up, that'd read 3x squared y squared minus 2x sine of xy, right, like that. And so this here is fy, and so then naturally fyy is going to be taking the partial with respect to y of this once more. And so it's a little bit tedious, but let's do it. So it's 6x squared y, and then minus 2x, right? Minus 2x, the constant, and then the derivative of sine is cosine xy, and again we take the derivative of this sine because inside it is a y, and so it's a function of y, and then times x. Okay, I needn't say that anymore, so we say we are done writing this. Now, if you look at the answer for fxx and fyy, clearly they're not the same, but there's some symmetry. And the next example, we will state a very important result called Clairaut's theorem, aka Young's theorem, about what happens if you do fxy and compare it to fyx, like this. Yeah? So there's an interesting thing to note about this here, and we're going to figure it out in the next example. Don't do it on your own, because then you don't have to watch the next example. Okay. But it's okay. If you're an inspired student and you're curious what has to be true about mixed partials. Okay, so to conclude, let's do this last guy, and for him, as I said, it's sufficient if we just do the partial with respect to x or y, one of the two. And maybe we've been doing the partial with respect to x one too many times, so let's do the partial with respect to y. Yeah? For this guy. Okay, so first notice that it might be useful for some of you to rewrite the function f of xy so that in this part you interpret it correctly as reading sine of xy, all of it squared, right? And then it's plus e to the xy over the natural log of xy, like that, right? Okay, cool. So then you see that the argument of sine has both x and y. So depending on whether or not you're taking the partial with respect to x or y, you will need to take the derivative inside here because, well, this here, sine is, it can be seen, it is, and it can be seen as a function of y, but it could also be seen as a function of x, right? And obviously when we're seeing sine here as a function of y, x is a constant, and when we're seeing it as a function of x, y is a constant. And here, since we're taking a partial with respect to y, we said this x is a constant, so this sine is a function of y. Okay, but then it's all squared, so we cannot forget the fundamentals of derivatives, so we start with that. So with the taking care of that power, so that would mean 2 times sine of xy, and then to the first power, and I probably could get away without writing that one, but I want to be very clear. And then the derivative of this, that's cosine of xy, and then times the constant here we said is x, so times x. And so that means we're done with this part. Okay, so plus, let me put a giant plus sign, and this plus sign right here is this plus sign right there, because notice that both e to the xy and the natural log of xy can be seen as a function of y or x. And so then what that means ultimately is that we need to do the quotient rule here. What I'm suggesting is this. What I'm suggesting is, since we're doing with the partial with respect to y here, if there was no y here, then e to the x is just a constant, so we don't have to use quotient rule. We could get around the quotient rule. But now we do have to do the quotient rule because, well, there's a y right there, and so the e is a function of y. It's not a function of y now. Now it's a function of y and the constant x, because again, we're taking the partial with respect to y. That part was very important to explain thoroughly. So let me start here, because fy equals 2, we said sine xy cosine xy times x. So let me lead with the 2x right there. Now it's too close to the sign, 2x like that. Okay, yeah? Okay, and then that plus sign, so plus, because we know the quotient rule involves a quotient, so I don't want to write something here and then put a denominator under it. Like, so now we're onto the quotient rule part right there. So that would mean the derivative of the top, so that's, we're doing with respect to y, so that's e to the xy times x, because x is the constant, right, times x, and then minus, and then, well, sorry, the derivative of the top times the bottom, right? So I was forgetting my quotient rule fundamentals there, my bad. And this is not a plus, Jesus Christ, come on, focus, Royce. Okay, minus, and then the top, you guys know the quotient rule, so, and then times the derivative of the bottom. So the derivative of the bottom is going to be 1 over xy times x, right? Because x is a constant, and notice that this happens, right? So, yeah, and then of course, all of this, and this is why I wanted to scoot it to the left, all of this divided by the bottom squared. Right? Okay, yes, it's very cumbersome. You could do a little bit of cleaning up, because this x canceled here. What you could do is put a y right here, right? And then put a y right here, and then now you have a common denominator that's a y on the numerator, so basically you could put that y right here. That's an algebra skill, and get rid of this, right? That's an algebra skill that I feel you should have, so we don't need to have a lengthy discussion on it. All right, cool. I'm satisfied with this, and yeah, I hope you are also. Keep watching. Next again is Young's theorem. Keep watching. Take care.